Hi, this is Professor Merrill Lichty. In this video, we're going to conclude our study of simple regression by making some comments and also looking at some of the assumptions. The first comment is about extrapolation. Extrapolation is any time that you use inference or prediction based on a regression model outside of the range of the x values. So in this case, we have our x variable is income, and we have values between about $14,000 and $60,000. Well, what if we wanted to predict the amount of spending by somebody who made $90,000? Well, we could use this regression line to do that, but we don't necessarily want to put too much faith in the outcome. Why? Because outside of that range, between $14,000 and $60,000, we don't really know what the data is doing. And so we could make the assumption that it's linear, but that's just a guess. And so you could do this, but you don't really want to, and rely on the results anyway. The next comment is on correlation versus causality. Correlation, you'll remember, is just the measure of the strength of the relationship between two variables. As one tends to go up, if they're positively correlated, the other is going to tend to go up as well. But that tendency is not a cause and effect relationship. A cause and effect relationship can only be established by an experimental design. However, oftentimes it makes sense to establish as a belief that there is a cause and effect relationship. As the steamboat example highlights or illustrates, if X is the income of a person who's going to go to steamboat, it makes sense that the higher the income, the more they're going to spend. Although the data does not necessarily establish that, we can say that it's pretty likely that there is a cause and effect relationship here. Here are a couple of examples of when correlation and causation are not the same thing. This is kind of a famous data set. Y is the Harvard professor's salary, and X is the crime rate in New York City. It turns out that these things are highly correlated for some reason. And to think of this as a cause and effect relationship doesn't really make sense. Think about what that would be saying. If a Harvard professor's salary increases, then the crime rate in New York City goes up, and vice versa. If the crime rate goes up in New York City, that causes the Harvard professor's salaries to go up. So this is what we call a spurious correlation, and there are lots of variables that are out there that are correlated with each other that don't have a cause and effect relationship. And if you search through enough variables, you're going to find some that are highly correlated and really have nothing to do with each other. Another example would be Y is the value of a family's car and X is the value of their home. You would think that these things are probably highly correlated. If you have a big fancy home, you're going to probably have a big fancy car. But to say that one causes the other is not really a correct thing to say. Imagine that if you wanted a more expensive car, if there is a cause and effect relationship, all you'd have to do is go buy a more expensive house. And that's not how it works. So what's going on here is probably some other variable or third variable that's driving both of these things, like maybe income or something like that. So you want to be careful about when you determine that there is a cause and effect relationship. It can't be done just by looking at the data. Usually you have to look outside of the data and really analyze what the relationship is between the variables. The next comment we're going to make is about the value of r squared, which is the coefficient of determination. And the question that often arises is what's an acceptable value for this? And that's a hard question to answer because it really depends on the context. So for example, 95% seems like a very high value of r squared, and it is, but sometimes it might not be good enough. And here's an example. If you were in a lab and you were trying to measure the pressure and the temperature of some gas or some condition, then you know that there's a linear relationship between these things, and the r squared value should be extremely high, even higher than 95%. So If you're getting back measurements that show that the R squared is only 95%, that's a little bit too low. On the other hand, we might have something that's very small that might be very informative for us. And an example of that is financial data. Oftentimes there's very large models that are generated that can capture a small proportion of the variation in the y variable and yet still be significant. And 12% might not be too small, or even 3 or 4%. If you think about the amount of money that's going into these types of models, then if you can increase your explanatory power by 12%, that can be pretty substantial. Here's our final comment, and it has to do with the t-test and the f-test that we talked about already for linear regression. We said that those are the same thing if we have the null hypothesis that beta 1 is equal to 0 versus the alternative that beta 1 is not equal to 0. So if those are equivalent to each other, why are we going to learn both of those? Well, it turns out that they can do different things. For example, with a t-test, if you wanted to do a one-tailed test, you could easily do that. Or you could test that the parameter is equal to some other value than 0. Beta 1 equals 4, for example. The f-test can't do that because you can't specify the mean value. All the f-test is looking at is the amount of variation. What can the f-test do that the t-test can't do? Well, this turns out to be a very important part of multiple regression. And when we get into that in the next unit, you'll see a little bit more in detail how that works. But basically, if we have more than one x variable, we can use an f-test to test whether all of those beta coefficients are equal to 0. And the t-test cannot do that. So, in summary, the t-test and the f-test are really only equivalent in simple regression when we have the null hypothesis that beta 1 is equal to 0 versus the alternative hypothesis that beta 1 is not equal to 0. Let's move on now and talk about the assumptions of simple linear regression. Remember that we have a model that says y is equal to beta 0 plus beta 1 times x1 plus an error term. And there are assumptions that we make about this that mostly have to do with the random error term, as you will see. The first assumption we have is that there's a linear relationship between the y and the x, and that it's properly specified. In other words, it's not quadratic or some other nonlinear function. The rest of the assumptions have to do with the error terms. First of all, we assume that the errors are independent of each other and that they're also uncorrelated. We also assume that the error terms are normally distributed, which probably shouldn't be a surprise to you. And in the long run, the expected value of the error terms is 0, which means the expected value of the y variable is going to be the line that we fit. The variance of the error term, sigma squared, is assumed to be constant for all values of x. This is also called homoscedasticity. And if one or more of these assumptions is violated, then we have to be a little bit careful because it's possible that the results of the regression will not be valid. So how do we check these assumptions? Well, first of all, we're going to do this subjectively by just looking at graphs. There are tests you can do to check a lot of these things as well. We're not going to get into those. Instead, we're going to just visually inspect what's going on. So from this plot, you can see that we have a bunch of data and we have the sample regression line, and it looks like it fits the data pretty well. So we'll say that we have established that there's a linear relationship between x and y. And then if I look at the variation of the data points above and below this regression line, it looks like it's fairly consistent. So we can say that the variance is constant. So again, most of the assumptions we've made here are about the residuals, or rather the error terms. And the residuals are just the estimates that we have for the error terms that come from the observed value yi and the fitted value yi hat. So we're going to call this the realization of the error terms. And if we look at the residuals, we can answer all the questions that we might have about the assumptions. So here on the left, again, we've got the data, so x versus y, and a straight line going through that. We've kind of already talked about the linear relationship being established there. And it looks like there's also constant variance. But to see even better what's going on, we can subtract the fitted values. In other words, fit the fitted values and subtract those from y. That gives us our residuals. And if we plot that versus the fitted values, we have this graph over here. So basically we're just taking this graph here and we're making the line, instead of on an angle, we're taking out the linear trend and making the line horizontal. So we can look at the trend then, and again, if you see something that just looks like random error, which is what this right side looks like, then you can say that we have constant variance and a linear relationship. And that's based on analysis of the residuals. Here's an example that doesn't quite look as nice as what we just had. On the left, we've got our scatter plot with a linear fitted line, and when we look at the residuals for that, again, we subtract off the fitted values from the y's and plot that versus fitted values. You can clearly see this nonlinear relationship here. So we would say that this does not meet the requirements for the assumption of a linear relationship. Here's an example of the violation of constant variance. You can see from the residuals over here that for small values of x, the variation is small as x gets bigger, even though it looks like y is getting bigger. Y hat is getting bigger, that's a function of x, remember. We get much more variation. And there's many different patterns you can see for this sort of thing, but we would look at this and determine that that assumption is not met, and this is called heteroskedasticity. The assumption of independence of the residuals is a little bit more difficult to deal with because there's lots of different ways in which the residuals can be dependent. Notwithstanding, we are only going to look at one of those, and that has to do with the time ordering, because this is the easiest way to determine if the residuals are dependent, at least in that regard. And if you don't have the order in which the variables were collected, or the samples were collected, then you can't really look at this. But the idea is to take the data, like what you see over here. Here's x and here's y, and if you look at this, there's no real patterns that show up above and beyond the regression line. But if we were to put those x observations in order in which they were collected, then we might see something that looks like this over here. And you can see that we have alternating residuals in terms of being above and below the 0 point. So here we're above, and then below, above, below, and we get this pattern that shows up, and it's alternating back and forth. That's what we call a negative autocorrelation, and that's one example of when the assumption of independence is violated. There are other patterns that you can look at. There's positive autocorrelation, and so that's going to be something that we want to check out. Here's the last assumption that we're going to check, and that's the one of normality of the error terms. And you can see that we have a histogram here that kind of looks like a normal distribution, except for that one spot over here where we don't have any data. And we can look at these things and get a good idea, but it turns out that when we're checking for normality, there's actually a test that we can run, and that's called the Anderson-Darling test. If we look at the normal probability plot in Minitab, we get these numbers for us generated for free. So we have a test statistic, sample size, and so forth, and a p-value that goes along with this test. Now remember, the null hypothesis is that the normal distribution is normal, and the alternative is that it's not normal. So the Anderson-Darling p-value here is 0.626, and we know what to do with p-values if they're bigger than the alpha level. In this case, let's say it's 0.05, then we're going to not reject the null hypothesis and conclude that we do in fact have normally distributed residuals. Okay, so let's look at an example using real data. This is trades data, and so y is going to be the number of trades executed, and x is the number of calls. This is back before computers, I guess, at least before internet and apps on your mobile phone to do trading, where you used to have to tell your trader to execute a trade. And in order to use Minitab, we're going to go to stat regression fitted line plot. You could also use stat regression regression, and we're going to say our response variable is trades and predictor variable is calls, and we're going to go to graphs, and this is what we need to do in order to look at the assumptions. First, we're going to say standardize the residuals and plot that, and then also give us a 4 and 1 plot. Then we're going to go to storage and say to store the standardized residuals, and this is what we're going to need in order to do the Anderson-Darling test. So click OK a few times and you get this output, and we see the scatter plot. Looks like there's a linear relationship. We've got the line fit there, and we can test whether it's significant or not by looking at the output of this F test. The F value is 56.21, which has a p-value of 0 to 3 decimal places, so that's pretty strong evidence to suggest that there is a linear relationship between these things. If we look at the 4 and 1 plot, then we can first of all check out the standardized residuals versus the fitted values, and again, this confirms that we've got a linear relationship. And we can also get a good idea of the variance, and it looks like it's fairly constant. Again, this is subjective, so you might have a different opinion about that, and that's okay. If we want to know about independence, we come down here and look at the observation order on the x-axis, standardized residuals on the y-axis, and we don't really see any patterns in here. It's jumping back and forth quite a bit. It's spending a good amount of time on both sides, and so we would go with the independence on this one and say that's okay. But remember, those are both subjective, and your opinion might differ than mine. When it comes to normality, we got the normal probability plot here and a histogram of the residuals, and we could look at those and get a good idea, but it's better in this case to use the Anderson-Darling test statistic. And so go to stat, basic statistics, normality test using stored residuals. And this is why we stored the residuals when we ran the regression. And you can see the again, normal probability plot here. And the null hypothesis is that the distribution of the residuals is normal. The alternative is that it's not normal, and the p-value in this case is 0.059, which if I'm comparing to 5% alpha level, then I would not reject the null hypothesis and conclude that in fact this assumption is met. The data, rather the residuals are normal, the error terms are normal. But you might say, well, 5.9%, that's pretty close to 5%. What if alpha were 10%? Then you would reject the null hypothesis. And at this stage in your statistics career, I would say just go ahead and go with alpha's 5%, even though it's close. When you get a little bit more advanced and take some other statistics courses, you'll learn that there are transformations and other things that you can do to fix up that assumption a little bit more, and we're not going to get into that in this class. So there you go. We'll see you later.